Yes, welcome back. Today we are going to be learning dimensions in physics. Today we are going to be learning what? Dimensions in physics. Dimensions in physics. And what is dimension, or what are dimensions? Dimension of a physical quantity indicates the way the fundamental quantities of length, mass and time are represented using the letters L, M and T. Is that clear? So what is dimensions? We can simply say that dimension of a physical quantity indicates the way the fundamental quantities of length, is it? Those are the fundamental quantities of physics from the last lectures we had. We have length, what? Mass, and what? Time. Are what?
Represented by the letters.
Are represented by the letters L, M, and T respectively. Is that clear? Is that clear? So dimension is simply dimension of any physical quantity indicates the way the fundamental quantities of length, mass and times are represented by the letters L, M, T respectively. You understand? Whenever you have any derived quantity, derived quantity is always made up of some fundamental quantity, isn't it? So the way they are arranged, using the letters LMT indicates the word dimension. Is that clear? Is that clear? So it can be used to indicate the fundamental quantities of a physical what? Quantity. So use it to indicate the fundamental quantities. Example is when we talk about speed. What is speed? Speed is what? Distance over what? Time. So how do we represent the dimensions of speed? We know that distance is the same thing as length, isn't it?
Yes.
Length. Because distance from A to what? B is the length from A to B, isn't it?
Yes.
So distance here is L.
Yes.
Time is what?
T.
So we can say that speed is the same thing as L, T, right, isn't it?
Yes.
Because all over division sign you can change it with this, isn't it?
Yes.
So this is the speed is equal to LT to power minus 1. So this is the dimension of what? Speed. Because we say that dimension is simply what? The way the physical fundamental quantities are what? Indicated or represented. So the fundamental quantities here are what? L and what? T. Is that clear?
Yes.
Is that clear? Another example is what? Acceleration. Another example is what? Acceleration. I would say that acceleration is equal to what? Velocity over what? Time. Isn't it? What is velocity? Velocity is what? L over T. Isn't it? Time is also what? Also divided by T. So this L over T is what? Velocity. All over T. Is it? So we can have what? L over what? No, this is actually L over T, which is velocity, divided by what? Time, which is the same thing as L over T times 1 over T. Isn't it? This is velocity over time. Velocity is already L over T, divided by the same thing as over time, isn't it? then this is still equal to the same thing. But here, if you want to change the division sign to multiplication, you have to, instead of writing t, you have 1 over what? T. So if you break this down, you have L all over what? T squared. Is it? And L over T squared is the same thing as saying L T to power minus what? 2. So this is the dimension of what? Acceleration. That is the dimension of what? Acceleration. L T to power minus 2. Is it?
Yes.
Is that clear?
Yes, sir.
So we say what? Acceleration is equal to velocity over what? Time. Which is equal to, velocity is what? L over T. Is that not the dimension of velocity?
Yes.
L over T divided by what? Time. This time. Which is the same thing as saying L over T times 1 over what? T. Which is the same thing as saying L all over T squared. Which is the same thing as saying L T to power minus 2. This is the dimension of what? Acceleration. Is that clear?
Yes, sir.
Is that clear?
Yes, sir.
Now we are going to do more difficult aspects of this dimension. But before that, we are going to learn about the application of what? Dimension. How do we use dimension? Application of what? Dimension. Application of dimension. Number one is we can use it to find the true relationship between what? Between physical quantities where the what? Where the correct what? Mathematical what? Relation or formula cannot be easily obtained. So this one way we use dimension. When there is a statement in physics and we don't actually know how to write the formula, you understand? We can use the knowledge of dimension to break down the statements into mathematical relations. You understand? Which is, we are going to do some examples. So one of the major applications of dimension is to find the true relationship between physical quantities where the correct mathematical relation or formula cannot be easily obtained. So if you cannot use mathematics to find the formula, you can actually use the knowledge of dimension to break it down. Is that clear? Number two application is that it helps to find the true unit. Is it? The true unit of a physical quantity. Dimension can help you in determining the units of any physical quantity. Is that clear? It helps in determining the appropriate unit of a physical quantity. You can say true or what? Appropriate. You understand? You can use the knowledge of dimension to find the appropriate unit of any physical quantity. Is that clear? So which is among what we are going to be learning very soon. So we are going to look at an example. We are going to look at an example of how to apply this dimension. So let's look at this example. examples in dimension. Number one, let's look at this. In an experiment, right along. In an experiment, a string fixed at two ends is plucked. It would be seen to vibrate. The velocity v of the wave produced depends on the 1. I. Tension F in the spring. 2. Length L of the vibrating string. And number 3 is mass M. This implies that the velocity of the wave produced is proportional to tension. Length of the string and its mass. But the nature of the proportionality of the velocity of the wave to the other physical quantities are not easily ascertained except by the use of dimension. So we are going to use dimension to solve this. So let me explain this question. In an experiment, a string fixed at two ends. So when we have a string that is fixed at two ends, this is the string and it's fixed at two ends, A and B. It's plucked. You go and plug this string here. It will be seen to vibrate. Once you plug this string, the string will start vibrating, isn't it? It will start vibrating. The velocity V, is that clear? Of the wave produced depends on the what? It depends on the tension F, length L, and what? Mass M, is it not? So the velocity with which this will move will depend on the tension, the length of the wire, the mass of the wire. isn't it?
Yes.
But how do you know this relationship? You don't actually know the real mathematical equation. So you make some assumptions, you put that this is equal to k. Instead of saying that, you can say that the velocity is proportional to F, L and M. But this is not a pure mathematical relation. So to remove this proportionality sign, you put equal to and put what? Constant k. Is it? But you don't know what the level of this, the degree at which each of these quantities affect it. So here you can put A, put B, put C, so that when you use dimension and solve out, you see the real actual amount of A, B and C that we have. Is that clear? So we are going to use dimension. We are going to use dimension to solve down this, to see the actual relationship between the velocity, the tension, the length and the mass in this physics.